Hello everyone, my name is Santosh and I am a student of Chemistry Honors first year. It is an audio video lecture on covalent bonding. Covalent bond is formed by mutual sharing of electrons between the combining atoms of the same or different elements. The atoms involved in the formation of a covalent bond institute equal number of electrons for sharing in order to acquire configuration of nearest noble gas. The pair of electrons which constitute the bond between atoms is known as bonding pair of electrons. If there is one bonding pair of electron between the two atoms, the bond formed is known as single covalent bond. On the other hand, two or three pairs of electrons between atoms constitutes a double or triple bond respectively. According to Lewis' concept, the covalency of an element is the number of electrons which its atoms contribute for sharing while forming a covalent bond. For example, the covalencies of hydrogen, oxygen, and nitrogen are 1, 2, and 3 respectively. Theoretical treatment of covalent bond. The simple picture of covalent bond does not tell us anything about many interesting questions such as arrangements of electrons in the molecules, the shapes of the molecular orbitals, energy levels in a molecules, etc. Like atoms, we can write the Schrödinger wave equation for describing the behavior of electrons in molecules. However, it is very difficult to solve the Schrödinger wave equation for molecules. The solution can only be obtained by using certain approximations. And there are two main approaches which are commonly used, and these are the valence bond theory VBT and second one is the molecular orbital theory MOT. Both these methods are based on the variation principle or method. The valence bond theory was put forward by W. Hitler and F. London in 1927. It was later improved and extended by L. Pauling and J. C. Slater in 1931. The basic assumptions of this theory are: first, the atoms do not lose their identity even after the formation of the molecule. The second one, the bond is formed due to the interaction of only the valence electrons as the two atoms come close to each other. The inner electrons do not participate in the bond formation. Third one is, during the formation of bond, only the valence electrons from each bonded atoms lose their identity and the other electrons remain unaffected. Fourth one is, the stability of the bond is accounted by the fact that the formation of bond is accompanied by the release of energy. The molecule has minimum energy at a certain distance between the atoms known as internuclear distances. Larger the decrease in the energy, stronger will be the bond formed. So energy is inversely proportional to stability. Resonance. It has already been studied in earlier classes that the concept of resonance or mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structures, each of which can explain most but not all the observed properties of the compound, the actual structure lies somewhere in between the various possible conventional structures. The various possible structures are called the contributing or the canonical structures, and the actual structure is called the resonance hybrid. The resonance hybrid is indicated by putting a double-headed arrow between the contributing structures. The concept of hybridization of two or more conventional valence bond structures to arrive at an entirely new and individual structure, which however cannot be depicted on paper in terms of conventional formula and is termed as resonance. One of the most well-known example of application of resonance is afforded by benzene. Since benzene could not be assigned any satisfactory valence bond structure which could explain all its property, it was proposed that benzene is a resonance hybrid of structures first and second. This implies that the structure of benzene is represented neither by first or second nor by second structure but lies somewhere in between the two. It is evident that in the resonance hybrid, the bonds which link the carbon atoms neither correspond to single nor double bonds. On the other hand, all the bonds are equivalent and intermediate between single and double bonds. This has been confirmed by X-ray diffraction studies which show that all the carbon-carbon bonds in benzene are of exactly the same length, which is in between that of carbon-carbon single bond and carbon-carbon double bond. The resonance hybrid structure of benzene has 151 kJ per mole of energy, less than either of the contributing structures. This represents the resonance energy of the molecule. It is the energy which is responsible for the unusual stability and remarkable behavior of benzene. Note: the concept of resonance does not mean that any one molecule of benzene spends a part of its time in structure 1 and the rest of time in structure 2. It also does not mean that some molecules of benzene have got structure first and others got second. What resonance means is that any one molecule of benzene always has the same single structure which is identical with that of any other molecule and is intermediate between the structure 1 and 2. Other example of resonance are like carbon dioxide. Carbon dioxide is considered to be a resonance hybrid of three contributing structures as shown here. The observed bond length of carbon-oxygen bond in carbon dioxide is 115 picometer, is less than that of carbon-oxygen double bond, that is 122 picometer, which can be justified in terms of its resonance hybrid structure. The second example is carboxylic acid. The acidic character of carboxylic acid is explained by treating the carboxylic acids as the resonance hybrid of the following contributing structures. Conditions for resonance. According to the general theory of resonance, the various conventional structure formulae contributing to the structure of resonance hybrid must satisfy the following conditions. The various contributing structures should differ from each other only in the position of electrons, that pi electrons and the lone pair of the electrons, whereas the relative arrangement of atoms or the atomic nuclei to be more precise and their state of hybridization must be the same. Note: it may be recalled that the existence of structures have the same molecular formula but different relative arrangement of atomic nuclei leads to the phenomena of isomerism. The atoms involved must lie in the same or nearly the same plane. The number of paired and unpaired electrons in each contributing structure must be the same. For example, CH2 CH double bond CH CH2 is not valid contributing structure for the butadiene, that is CH2 double bond CH single bond CH double bond CH2, since it has more unpaired electrons than the other contributing structures. Fourth, all the contributing structures must show the correct number of the valence electrons. For the elements of second period, no contributing structure should have more than 8 electrons in the valence shell of the element. For example, CH2 CH double bond NS3 cannot be considered as contributing structure since in it nitrogen has 10 electrons in the valence shell, which is not possible. Fifth is all the contributing structures should have the same or nearly the same amount of energy and stability. Sixth one is when the contributing structures differ in energy content or relative stability, the more stable structures makes greater contributing towards the resonance hybrid. Seventh is in determining the relative stability of contributing structures, the following points may be noted. First is the larger number of covalent bonds in a structure, the greater the stability. Second is the structures involving separation of positive and negative charge are less stable than those which do not involve any separation of charge. Third one is when atoms of different electronegativities are involved, the structure having negative charge on more electronegative atom and positive charge on less electronegative atom are relatively more stable than the other way round. Fourth is the structures having like charges on adjacent atoms are highly unstable. Eighth point, the more the number of contributing structures, the more stable is the resonance hybrid. Properties of resonance hybrid. First, stability. A resonance hybrid is always more stable than any of the contributing structure. The extent of greater stability of the resonance hybrid depends upon the number of contributing structures and their relative stability. Second is resonance energy. It is a measure of stabilization due to the resonance and may be defined as a difference in energy between the energy of the resonance hybrid and its most stable contributing structure. Greater the resonance energy, greater is the stability of the resonance hybrid. For example, the resonance energy of benzene is about 151 kJ per mole. The value of resonance energy can be determined from the data involving heats of hydrogenation and heat of combustion, etc. Bond length. In a resonance hybrid, the bond lengths are different from those in contributing structures. For instance, the carbon-oxygen bond length in carbon dioxide is 1.15 angstrom or 115 picometer as against the value of 122 angstrom or 122 picometer for a carbon-oxygen double bond length. It may be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electrons. It is the delocalization of electrons which leads to the formation of stronger bonds and more stable molecules. Therefore, the term delocalization energy is often used in place of resonance energy. Resonance effect. It is a process of permanent displacement of electrons in a molecule brought about by resonance or the mesomerism, generally designed or as R or M effect. Unlike inductive effect, resonance or the mesomeric effect is transmitted through the pi electrons and operates in unsaturated system, particularly those containing a suitable atom or group in conjugation with unsaturated system. For this reason, it is also termed as conjugative effect. The main limitations of the valence bond theory are: the valence bond treatment could be applied successfully to only a few simple systems. In most of the system, the mathematically treatment involved is very difficult and we have to use approximate methods. Therefore, VBT treatment is inadequate in many systems. This theory assumes that the two electrons of the shared pair constituting the intermolecular bond must come from two different atoms. Therefore, the formation of coordination valency could not be explained by this method. It fails to explain bonding in electron deficient compounds. For any molecule or ion, we have to write several resonating structures, and even then we say that the true structure is none of these but a resonance hybrid of these structures. It is not possible to write one structure which can explain all the structural feature of that one molecule or ion. According to this theory, the atoms in the molecule of oxygen should have electronic configuration resembling neon. This would make the molecule diagmagnetic as oxygen O2. However, oxygen molecule is paramagnetic, indicating the presence of two unpaired electrons. This theory fails to explain the paramagnetism of oxygen molecule. Though valence bond theory has some limitations, yet it finds wide applications. It is frequently used as a qualitative guide in predicting the geometry of molecules or ions. Valence shell electron pair repulsion theory, the Vesper theory. Valence shell electron pair repulsion theory is the simplest theory for predicting the geometries of molecules. It is based on the repulsive interactions between the electron pair in the valence shell. This theory was proposed by Sidgwick and Powell in 1940 and was finally developed by Gillespie and Nieholm in 1957. According to this theory, the shapes of molecules can be determined by the number of electron pairs in the valence shell of the central atoms. These electron pairs experience electrostatic repulsions from one another, and the bonded atoms in a molecule adopted that particular arrangement in space around the central atom, which keeps them on the average as far as apart as possible. Postulates of Vesper theory. The main postulates of Vesper theory are: first, the geometry of a molecule depends upon the number of valence shell electron pairs, whether bonded or not, around the central metal atom. In the formation of a bond, the central atom shares its valence electrons with the surrounding atoms. However, in certain cases, all the valence shell electrons may not take part in the bond formation. The electrons left in the valence shell without forming bonds exist as lone pairs. For example, in methane, CH4 carbon uses all the 4 valence electrons in forming 4 bond pairs. On the other hand, in water, the central oxygen atom has 6 valence electrons. The hydrogen atom shares 2 of these 6 valence electrons in bond formation, leaving 4 electrons, 2 lone pairs. Thus, in methane, there are 4 bond pairs around carbon, while oxygen in water has 2 bond pairs and 2 lone pairs around it. According to Vesper theory, it is the total number of electron pairs that determines the geometry of the molecule. Second one is electron pairs tend to repel one another because their electron clouds are negatively charged. As a result, the electron pairs try to stay as far apart as possible to acquire a state of minimum energy or maximum stability. Repulsion between the lone pair and lone pair of electron is different than that between the bond pair or one lone pair and one bond pair. The repulsive interaction decreases in the order lone pair, lone pair, lone pair, bond pair, and bond pair, bond pair. The presence of lone pair in addition to bond pairs will result in certain distortion in the regular geometry of molecule. Fourth is repulsive forces decrease sharply with increasing angle between the electron pairs, and they are strong at 90 degree, much weaker at 120 degree, and weakest at 180 degree. Regular and irregular geometries. The molecule in which the central atom is surrounded only by similar bonded electron pairs will have regular geometries, while those in which the central atom is surrounded by bond pairs as well as lone pairs will have irregular geometries. For example, molecules such as CH4, BF3, PF5, SF6 have regular geometry because the central atom in these are bonded to similar atoms and there are no lone pairs in these molecules. On the other hand, the molecules such as CH2, Cl2, CHCl3, etc., in which the central atom is bonded to different atoms, and the molecules such as NH3 and H2O, which have lone pairs as well as bond pairs, have irregular geometries. Depending upon the number of electron pairs, the molecules have different geometry given in the table. It may be noted that the presence of lone pair disturbs the geometry as already discussed in the case of hybridization. Geometries of molecules containing different electron pairs according to Vesper theory. Geometry linear, bond angle is 180 degree. Examples are BF2, BCl2. Geometry trigonal planar, number of electron pair 3, bond angle 120 degree. Example BCl3, BH3. Number of electron pair 4, geometry tetrahedral, bond angle 109.5 degree. Example CH4, CCl4. Number of electron pair 5, geometry trigonal bipyramidal, bond angle 90 degree and 120 degree. Example PF5. Number of electron pair 6, geometry octahedral, bond angle 90 degree. Example SF6. Number of electron pairs 7, geometry pentagonal bipyramidal, bond angle 72 degree 90 degree, and example is IF7. Applications of Vesper theory. Vesper theory provides a simple approach to predict the shape of molecules. The results obtained the basis of this theory are quite in agreement with those obtained from hybridization concept. This theory is very simple to use. In this theory, no distinction is made between S and P electrons. We take into account only the number of electron pairs present in the valence shell of the central atom. The basic point is that the electrons pair try to remain as far apart as possible to get the stability. MOT, molecular orbital theory. Molecular orbital theory was developed by Hunt and Mulliken in 1932. The basic idea of molecular orbital theory is that atomic orbitals of individual atoms combine to form molecular orbitals. The electrons in molecules are present in those molecular orbitals which are associated with nuclei. These molecular orbitals are filled in the same way as the atomic orbitals in atoms are filled. Molecular orbital theory is based upon the following assumptions. A molecule is considered to be quite different from the constituent atoms. All the electrons belonging to the atoms constituting the molecule are considered to be moving along the energy molecules under the influence of all the nuclei. Just like an atom, molecule has orbital of definite energy levels. These orbitals are called molecular orbitals. The molecular orbitals are formed when the atoms to be bonded come closer together. Atomic orbitals of these atoms merge into molecular orbitals. Thus, the molecular orbitals associated with nuclei of all the bonded atoms in a molecule. The shapes of the molecular orbitals depend upon the shape of the combining atom orbitals. Difference between an atomic orbital and a molecular orbital. An electron in an atomic orbital is under the influence of only one positive nucleus. On the other hand, an electron is a molecular orbital is under the influence of two or more nuclei depending upon the number of atoms present in the molecule. Differences between bonding and anti-bonding molecular orbitals. The main points of difference between bonding and anti-bonding molecular are bonding molecular orbitals. Bonding molecular orbital is formed by the addition of overlap of atomic orbitals. It has greater electron density in the region between the two nuclei of bonded atoms. The forces in this orbital tend to bring the two nuclei of the atoms together. Therefore, the electrons in the bonding molecular orbitals contributes to attraction between the two atoms. It possesses lower energy than the isolated atomic orbitals. Anti-bonding molecular orbitals. Anti-bonding molecular orbital is formed by the subtraction of or overlap of atomic orbitals. It has lesser electron density in the region between the two nuclei of the atoms. The forces in this orbital push the nuclei apart. Therefore, the electron in the anti-bonding molecular orbital contribute to repulsion between the atoms. It possesses higher energy than the associated atomic orbitals. Comparison of valence bond and molecular orbital theory. The valence bond theory and MOT are the two basic approaches to explain the structure and bonding in molecules. They have some similarities as well as differences. These are given as similarities of valence bond theory and MO theory. Both the theories are approximations. Both the theories take into account the overlapping of atomic orbitals. The strength of the bond depends upon the extent of overlapping or interaction. The basic principle involved in the distribution of electrons are similar. Thus, an orbital, whether atomic or molecular, cannot have more than two electrons, the Pauli exclusion principle. They are filled in the order of increasing energy, a Gauss principle, and if there are more than one vacant orbital having the same energy, they would first be filled singly. Hund's rule. In covalent bond formation, the essential interaction according to the both theories, sharing of the bonding electron density by both nuclei, both the theories predict the concentration of electron density between the nuclei. Both the theory predict that for bonding, the atomic orbitals must overlap and have appropriate symmetry about the molecular axis. Both the theories account for directional nature of covalent bond. Point of difference. Some important point of differences are summarized below. Valence band theory. It starts with individual atoms and considers the interaction between them. Electrons in molecules are localized as if they are present in isolated atoms. The atoms retain their individual identity. Resonance is an integral part of valence bond theory. For most of the molecules, VBT underestimates the ionic term and does not give it much importance. It cannot explain the paramagnetic nature of O2 molecule. MO theory. This theory starts with the nuclei of the constituent atoms. It treats the nuclei of the molecule as polycentric and then construct the molecular orbitals. The atoms lose their identity. It does not involve the concept of resonance. The MO theory overestimates the contribution of ionic terms in its total wave function and it explains the paramagnetic nature of O2 molecule. And this is how we are now able to understand VBT and MOT, which are the most important theories in covalent bonding. Thank you.